This is Chapter 13 on least squares data fitting, which is one of the most important applications of least squares we'll see. Okay, so the setup is this. We have a scalar y, and we have an n vector x. And we believe that there's some functional relationship between them, meaning we believe that y is approximately equal to f of x. I'll say a little bit more about that later. So here, x is called the independent variable. This is a traditional name for it. And y is called the outcome or the response variable. Now, this function f tells you how x and y are related. Now, often x is a feature vector, so it's a vector whose entries are features associated with attributes of some item. And then y is something about that item that we want to predict. So that's the most common setting here. Now, we don't know f, this function, which gives the quote true unquote relationship between x and y. And the truth is there usually is no such f, right? That it simply, we have some data and we simply want to fit a model that approximately predicts what y is given x. So, but sometimes there's a true model or something like that. Certainly when we experiment with methods, we will do it with data that we generate ourselves, and then there's a true model. But in most applications, there's no such thing as f doesn't exist. It's a fantasy. Now, we're going to be building our model or data fitting methods based on some data. And so data, we're going to have a set of capital N data points, and they're going to be x1 superscript 1 up to x superscript capital N. Those and the associated outcomes, those are the independent variables, and the associated outcomes are going to be y1 up to yn. And we're using superscript here to index which of the data examples we have, right? So we refer to x superscript I, y superscript I as the ith data pair. And if you want to refer to a component in x, you would have x superscript I sub j. That's the jth component of the ith data point. So this is a data set, it's called. And what we're going to do is we're going to try to build an approximate model using this data set. Now our model, we're going to denote by f hat. And as I've said before, it is in applied math, it is kind of a convention that hat means an approximation of something. So the idea here is f hat is supposed to be an approximation of f, this true function, which in fact probably doesn't even exist anyway. But the idea is that this thing is supposed to guess or make an approximation of y is given x. Okay, so we'll be focusing on a very simple set of a very simple model form in which f hat of x is equal to a linear combination of f1 of x up to fp of x with coefficients theta 1 through theta p. Now these f's, these fi, f1, f2, f3, those are so-called basis functions, and we're going to choose them. And we'll say a little bit later about how would you choose them and why would you choose them one way or another, that kind of thing. These are the basis functions. And then theta I are the model parameters that we choose, right? So the idea is first you pick the basis functions, and then you choose the model parameters, right? Which are just numbers. They're theta 1 up to theta p. Now here, the way we interpret it is this, is if I is in general, y hat equals f hat of x, this number, y hat, is our guess as to what the y, the outcome or label associated with x would be. So this is our guess. And of course, we can have a drum roll and reveal y and y hat and just see how close we are. Okay, so if we look at our known data, f hat of xi is y hat I. We're going to call that's our prediction of what yi is. Now that's in our data set. So the truth is we know we know this. That's a number, and we know this number. And we can, of course, what we'd like, I mean, ideally, we'd like them to be, well, equal. Then I'd have a perfect predictor of what's happening. So, but we're going to see that that's, for a number of reasons, not a good idea. But nevertheless, so what we're going to do is we're going to actually back off and say that we want actually what we'd really like is the predictions to be close to the true values. We'll get to what we'd really like shortly, actually in the next section. Okay, so this brings us to least squares data fitting. So the prediction error or residual on the ith data point is the true value minus the predicted value. So that's it. But by the way, some people reverse it the other way around and so on. But it's actually not, for us, it's not going to matter. So least squares data fitting says this: choose the model parameters theta I to minimize the RMS prediction error on the data set. And that's simply the sum of the squares of the residuals divided by n. There's capital N of them, and then you take the square root. So that's root mean squared. Now that's the RMS error on our prediction set. And remember what each of these is. Each of these is the difference between the true value and what you predicted, right? So if this is small, you would say that your model is pretty good. If it's large, your model is, well, pretty poor. Now, this method of choosing the parameters theta, this can be reduced to a least squares problem, and therefore we can easily solve it, even when these are quite big. So let me explain how that works. So let's express our data set, and we're going to have several things. We're going to have yi, that's actually the true observed labels, or sorry, outcomes. We'll have y hat I, that's what our model is predicting. Now, y hat I is a function of our thetas. I mean, it's also a function of the choice of f's, but we're assuming that the choice of the basis functions is fixed, right? So y hat I is our prediction on the ith data sample. And then Ri, of course, is the difference of the two. It's the residual or prediction error, lots of other ways to call it. And these are going to be n vectors, and that means that the jth entry of it is the jth is the error, and it is the outcome, prediction, and residual or error on the jth data example. Okay, so these are now vectors. Now, if you look at RMS of the superscript d means data on our data set. So the RMS value of RD, that's just the RMS prediction error, and that's what we want to minimize. We want to choose the thetas to minimize that. So we're going to form an n by p matrix A, and the elements are going to be aij equals fj of xi. So it's the jth basis function evaluated at the ith data point, the independent variable value, right? And so with this definition, we get a very compact matrix vector equation. It says our predictions are equal to this matrix A multiplied by theta. So this makes it very clear, by the way, how the predictions depend on theta. And what we see is it's linear in this case. Now, that's why we call it a linear in the parameters model, because the predictions are linear functions of the parameters. Okay. Now, of course, once we choose the parameters, they don't vary, and it's not relevant that your model is linear in the parameters anymore. But nevertheless, that's it. Okay. So least squares data fitting says please minimize the RMS value. That's the same as minimizing the norm squared. So of RD, but that's yd minus y hat d norm squared. And that's equal to this. And we quickly get it. We have moved it around, and we now have a least squares problem. So that's it. Now we know everything. We then know that, in fact, the optimal theta, this is assuming that the columns of A are linearly independent. Okay, assuming that's the case, then theta hat is A transpose A inverse A transpose Y. That's a formula for it. In fact, we don't compute it that way. We would compute it by, let's say, a QR factorization, as we saw last time. Also, I should say in most languages, this would look like this. It would simply say that theta hat is A backslash YD. Now, what I do want to remind you of is that is not mathematical notation. That is code. So if you're among friends or something like that, or people who know about this, you can write that down. But don't write that or mention that if you have friends who are mathematicians or something like that. So, so that's it. So basically, this page can be implemented very shortly. Basically, it says the first thing you do is you create the matrix, number one. Then you do this. And then you get your parameters, and now you have your prediction model. Now, if I take a theta hat minus y squared, that is the smallest norm squared value that can take. And if I divide by n, that's called the minimum mean square error fitting error. And I think it's minimum mean square error, MMSE. So you will see that you'll see that several places, right? The idea of MMSE. Everyone will just assume you know that acronym. Okay, so what we're going to do now is we're going to look at at essentially the simplest possible prediction model or model. And it's a constant model, and that's obtained. It's crazy. It goes like this. I have one basis function only, so p equals 1. And here's my first basis function. It's f1 of x is equal to 1, always, period. That's it, just 1, okay? And so the model is, well, it's theta 1 times f1 of x, but f1 of x is 1, so it's just theta 1. And so this is a fancy way of saying our model is just a number. Here's our prediction model is, you would say, what do you think the demand for XYZ is going to be tomorrow? And you say 13.1. And you go, then the next day they come back and they say, what's the demand for blah, blah, blah? And you'd say 13.1 and so on. So the idea is it's a pretty simple model. It's simply a constant. That's it. Okay. So we can actually just work it out from the formula. So here A is simply the 1's vector, right? It's P equals 1, so the width of A is only 1. And in fact, what you're supposed to plug into this matrix A is the value of that basis function at that data point, but that's always 1. So A is simply the vector of 1's. Well, here's the formula. It's just theta transpose theta inverse, theta, 1 transpose 1 inverse, 1 transpose YD. But 1 transpose 1 is just n, capital N. It's the number, right? Because it's a sum of n numbers, each of which is the product of 1 and 1, otherwise known as n. So what this is, and 1 transpose YD is the average. It's the sum of YD. So this is the sum divided by n. That's the average. And that's really cool. So it says, and in retrospect, it's extremely intuitive, right? What it says is that if you want to use a constant model to summarize or predict some data, you should simply look at the mean of what that data has been and guess that, right? So if you want to guess the temperature in Palo Alto, let's say, well, based on nothing as a constant, you would simply take the mean, and you'd say that's what it is. Okay, that's the temperature. Okay, now interestingly, the minimum mean squared error is the standard deviation of YD squared, right? And so the RMS error, the optimal RMS error is the standard deviation. So this is actually a very good interpretation of what the standard deviation is. So if I tell you that I have some data YD and I say, well, the mean is 5 and the standard deviation is 2. I mean, you can understand that by itself, right? It means that basically, roughly speaking, YD is kind of above 5 and below 5 about equal amounts. That's false, but just roughly. And it also tells you that it varies from 5 by about plus minus 2. So we would not be surprised if we saw a 5 in that or a 7. Of course, we can have a larger number of larger deviations from the mean, which is 5. But that's the rough idea. Okay, and so another interpretation of that is simply to say that guessing 5 is the best constant predictor for that variable y. That's one way to say it. And if you do that, if you use that constant model, which is the simplest model you could possibly have, the RMS error is the standard deviation. So I should say that sophisticated models, which we are shortly going to be looking at, all basically must be judged against this simplest model. It doesn't make any sense, right? If someone walks up to you and says, "Oh, I've created this incredible thing. I've been working for days on putting a model together and blah blah blah," and my RMS error is like 0.2, and you go, "Cool, dude, that's great." And you go, "By the way, what was the standard deviation of the data?" And if they say, "Oh, 0.22," then you can say, "Look, you did basically nothing, right?" So because the constant predictor is not a whole lot worse than your complicated predictor. So anyway, so this is a very important point. It's actually something a lot of people, well, unfortunately, some people don't do. But this is what puts everything in context. It's your baseline model, always.